All right, here we are for another rotation free response problem. This one's from 1985, which is really old. That's before I was even in high school. I was in junior high. It says here, we have this pulley of mass 3m and radius r mounted on a frictionless bearing supported by a stand that has a mass 4m. And it says, the moment of inertia of the pulley around its axis is 1.5 mr squared. You say, hey, gosh, that would be like 1/2 the mass, 3m, times radius squared. That's just the moment of inertia of a disk. Okay. Passing it over the pulley is a massless cord supporting the block of mass m on the left and mass 2m on the right. Again, why is that cord massless? Because otherwise, as this thing moves, you'd have more and more mass on this side pulling. And so that force, that net force would be changing, that total force on the system. And so your acceleration would be changing. It'd be awkward. But it's a massless cord, so we don't have to worry about that. Let's see here. Mass m on the left, 2m on the right. So we know that it's going to want to accelerate this way because I have more force pulling down on the 2m side than on the m side. The cord does not slip on the pulley, so after the block pulley system is released from rest, the pulley begins to rotate. Draw force diagrams for these guys. I'm going to do this on separate paper, so I've got plenty of space. All right. So taking a look at this, you'd say, they want force diagrams for the two blocks. So here is that block M. Here is that block that has a mass 2m. And you say forces. Well, ranged forces. I'll have a gravitational force here, mg. This would have a gravitational force of 2mg. Contact forces, the only thing touching them is the ropes, and those are stressed, so there'd be tensions. Let's give these names. I'm going to call this one T1. I'm going to call this one T2. I don't know, why not? It's the tension on the 2m guy, the tension on the 1m guy, I guess. I could also go left, right, or whatever. Okay, now that's it. There's nothing else touching them. So that's it. That's part A. Okay, part B. They would like us to use the symbols that we used here, so the names for the variables we used here, to write out first the equations of translational motion, Newton's second law, for each of the two blocks. Newton's second law, we should know that's the most important formula in physics, sigma F equals ma. So I'm going to do that for both of these guys, using the variables that I assign there. Now I realize that if I do that, I need to choose what direction I'm going to call positive. And I'm going to be consistent throughout the problem. Since I know this is the bigger mass here, I know this is going to be accelerating it this way, right? Okay, they're at the same radius, so they have the same lever arm, but this will have more force. So I think I want to call this way, okay, to the right over it, so into the page with my thumb as I curl around, that into the page be the positive direction. So if I do that, to be consistent here, I'm going to be calling this way positive. So on this guy, I'll be doing T1 minus mg. Okay, is ma. And on this side, calling this way positive, it'll be 2mg minus T2. And now be careful, the mass on this side was m, the mass on this system is 2m. So this will be 2m times acceleration. Those accelerations will be the same because we're tied together, right, by this non-stretching rope. And so it's however far this one moves, that moves same. They're going to have the same velocities and accelerations. Okay, so that was BI. BII says, write the analogous equation for the rotational motion. That's the rotational version of Newton's second law. That's sum of the torques is I alpha. So for part II, I'm going to use the sum of the torques is I alpha for the pulley. I really ought to have a little force diagram for the pulley to do that. I'm wishing now I had left some space in the middle to draw it. I'm going to have to draw it off to the side here. That's life. So if I look at the pulley, we'd say what forces are going to act on that? Well, there'll be this tension here from the rope on the left. That's T1. That's going to be the same size as the tension there. It's the same rope. And I'll have a tension here, T2. The only other, you say the other thing is there's going to be a ranged force, right? Be gravitational force, mass of the pulley times g. Now the mass of the pulley is 3m, so we could call that 3mg. And there'd be a normal force from the axle pushing up. And that's my forces on the pulley. And we want to do a sum of the torques. So again, we're going to call over the top this way positive torques. So it'd be the torque caused by T2 minus the torque caused by T1 is I alpha. You say, what about these two forces? They're not going to exert torques because they're acting at the axis of rotation, so they have no lever arm. When I go to calculate my torques, we know that the formula for a torque is R cross F, and these forces, their R value is 0. Their R is the distance from the axis of rotation, and they're right at the axis, so it would be zeros. So no torques from those. That's it. Are my two torques, T2, torque 2 minus torque 1. Let's go ahead and let's see here. Is that, you see, now they want me to use the variables from the diagram here, so I can't leave it as torque. I got to rewrite it in terms of what's given. Right. So, so what I'm going to do is I'm going to use my torque as R cross F. So this will be R times T2, right? Okay, and I'd have, there'd be like a sine theta in there, right? The thing is that our R vectors start at the axis and go to where the force is applied. Because ropes come off, when they're under stress, they come off tangent, and this is a radius, they're going to be 90 degrees off. So it'd be like a sine of 90 there, which is just going to be 1 when I do my cross product. Okay, there's like a sine theta in there, where theta is the angle between R and F. All right, same thing's going to happen over here. Okay, that's that same size R, right, on the circle. And so that's, again, 90 degrees, R cross F. So R cross T1 is, I'm going to have just R times T1 times the sine of 90, which is 1. All right, my I, we already know this equation is being written for this pulley, and we know the I for the pulley. They already told us it was 1.5 mr squared. I'm just going to write that as 3/2 mr squared because I'm a big fan of fractions. So that's it. Now, the only variable that's showing up in here that's questionable at all is R. R was given to us in the problem. It's not on this diagram specifically, but we need it. There's no way to get rid of it. And it was a given variable there, so I'm okay with leaving it in there. All right, so I believe that these three equations here are what they're asking for in part B. All right, which takes us to part C of this problem. They'd now like us to solve the equations we came up with in part B for the acceleration of the two blocks. Okay, you say, well, the two blocks, they're tied together, right? It's the same rope between them. However far this moves, that'll move the same. They'll have the same velocities, same accelerations. So it's just the one acceleration that they both have. And they want A, the acceleration. We're talking about a linear acceleration here for the blocks. So we're actually trying to solve this A here, they're the same, right? That's the acceleration of the blocks. So looking at this, you say, I'm now going back to like the variables that were given to me in the problem. They didn't give us these T's, these tensions, so I got to get rid of them, right? And the only other equation I have that has T1 and T2 in it is this equation here for the torques. So I'm going to do some subbing around here. I'm actually going to go ahead and I think, oh, holy cow, that's the I left out the alpha. Ooh, whoops. There's an alpha there. Sorry about that. All right. Anyway, get on to this part C. So what I'm going to do is I'm just going to go ahead and solve this equation for T1 and substitute it in where I see T1 there. Solve this equation for T2, substitute in where I see T2 there, eliminate those two tension variables. All right. If I did that, let's see here. I'm just going to squeeze it in here. If I rearrange this, you can see this is T1 is going to be mg plus ma, right? If I rearrange this one for T2, we'll get that T2, what? Yes. T2 is going to be, I'd move that over there to become positive. I have to move that over there. It's going to be 2mg minus 2ma. All right. I'll be substituting those in here. So I'm going to have r, and instead of T2, I'll have this expression. 2mg minus 2ma minus r times T1, where T1 is mg plus ma. And that'll be equal to 3/2 mr squared alpha. All right. So now I have a line with variables that were given to me except a, which is what I'm trying to solve for, but there's an alpha there too. Because the cord does not slip on the pulley at all, right? The cord, they tell you that it doesn't slip. Then we know that however far this cord goes, that's how far a point on the rim here would turn, right? So I can go ahead and say, well, if I know the angular acceleration of this, I can calculate the tangential acceleration of this using a as our alpha. So where it says alpha, we can substitute in so alpha is a over r. Okay, so we'll put that substitution in there. And now we'll have an equation that just has one unknown, a. Okay, and we can solve for that acceleration. Let me go ahead and I'm going to go ahead and distribute out things here and kind of tidy this up a little bit. So moving along here. Let's see here. Well, first of all, before I even do that, I'm just going to do this. I'm going to substitute in that a over r. So I have 3/2 mr squared times a over r. You know that this r down here is going to cancel one of those r's in that r squared. Now there's an r in this term, an r multiplying this term, and r multiplying. So I can divide through by r. All the r's go away. Awesome. Okay. I can see there's an m in this term, an m in this term, this term, this term, this term. All the m's drop out. Sweet. All right. So we are tidying this up rapidly. All right. Let's now see what we've got. Okay. After doing all that, I'm going to have 2g minus 2a minus, now let's distribute the minus to both terms, minus g minus a. On this side, I've got 3/2 a. Look at that. Look how simple this is becoming. Okay, so let's see here. We want to get all the a's together. This is minus 2a minus, that's minus 3a. When I add to the other side, I have 3a. 3a plus 1.5a, that's 4.5a, right? Or 9/2 a, if you will. On the left side, I've got 2g minus a g. That's just g. So rearranging, 2/9 g is my acceleration. Ta-da! All right. So that's my answer for part C of this. Okay. Next, they would like us to, now that we have the accelerations, can you find the tension in the segment of cord that's attached to the block of mass m? In other words, for us, we called that T1. So they want us to find the size of T1. You say, hey, look, up here, we have an expression we came up with. T1 is mg plus ma, and now we know how big a is. We'll just put that in there. Bam, we have it. So part D, you say, that's not going to be bad at all. I'm just going to grab that expression that we figured out before. I would get that T1 is mg plus ma. And where it says a, we're going to put in that 2/9 g. So T1 is mg plus m times 2/9 g. So that's a 1g and a 2/9 g. That's 11/9 g. at 11/9 mg. Right, yes. Is that okay? Hope that's okay. So 11/9 mg, you say, now wait a minute. Wait. How heavy is this guy? Well, it's got a mass of mg, but this tension now is 11/9 mg. That's bigger than mg, which means this will accelerate up. And you say, yes, that is exactly what's supposed to happen. This heavier weight yanking on it is going to accelerate that one upward, right? Okay, and that makes sense. That makes sense. Okay, we've got one last part to solve, and that is they would like to know the normal force exerted on the apparatus by the table when the blocks are in motion. So we want to know, how hard is the table pushing up on this while the system is accelerating like that? Okay, I find this part really kind of interesting to think about. A lot of people's first gut instinct is to say, well, let's just take the weight of all this, gravity pulling down. This stand isn't going anywhere, so surely the weight of everything pulling down will be balanced by the weight pulling up, pushing up, for normal force pushing up. You say if you add it all up, you'd have m and 2m, that's 3m, plus 3m for this, that's 6m, plus the stand is 4m, 10m. And so you would figure how gravity is going to pull down with 10 mg. So wouldn't the floor have to push up, or whatever this table have to push up with 10 mg? But that's not going to be the case. All right. So to explain why, you would say, look, if this whole thing was sitting still and was steady and nothing was accelerating anywhere, then yes, the forces would have to balance out. Treating this whole thing as one big system, I would have the only outside forces are gravity and the normal force. And if it's sitting still, then yeah, that would balance. But they're not sitting still. This part is accelerating up and this part is accelerating down. Do you see how more mass is accelerating down than is accelerating up? So overall, we have an acceleration down here for this whole system. If I think about maybe the center of mass of the system, as this accelerates down and a smaller amount of mass goes up, the center mass of the system will be accelerating down, won't it? So the net force on the system cannot be zero because we have an acceleration down. Okay? So that normal force up, we're expecting it to be smaller than the total force down, smaller than 10 mg. Okay, and we'll double check that at the end. All right, so this is, you say this is tricky then. One way of solving for this would be to look at the whole system and calculate the acceleration of the center of mass and say my total force equals ma, right? Let's do it that way first, and then I'll show you another way of solving it that you may like better. I'm a big fan of the center of mass way, though, because, well, I think it's kind of neat to think about the fact the center of mass of the system is accelerating down. So here we go. So how do you find the acceleration of the center of mass? Because what I'm going to end up doing is doing a sigma F equals ma for my system being both blocks, the pulley, and the stand. All right. Okay. So both blocks, the pulley, and the stand. That's M and 2M, the 3M pulley, and the 4M stand, right, supporting it. So if I do that, then I would have a normal force up from the floor, from the tabletop, right, rather. Okay, and that's the force we're trying to find, minus 10 mg, right? That's the gravitational force on that whole 10m system, would be equal to the mass of the system, 10m, times the acceleration. Now, the whole system, how do you put an acceleration value in the whole system? You use the acceleration of the center of mass. Okay, so how do we find that acceleration of the center of mass? Well, you may recall that our center of mass formula is that position of the center of mass is the sum of all the masses times their positions, mi's, xi's, right? Divided by the sum of the mi. Okay, the sum of the mi, that's just the total mass. Okay, that's just m total. So you might remember that I moved that over there, and I said, hey, mass total times the position of the center of mass is equal to adding up all the little bits of mass in the system times their positions. So in other words, instead of worrying about center mass and saying, oh, I got this little mass here and this little mass there and adding up and plus this little bit of mass here, this one, I can just treat it as if all the mass was at the center of mass. Okay. What we did next is we took the derivative with respect to time of both sides. Mass, of course, isn't changing. So it's really just mass times the derivative position. You know what that is. Derivative position with respect to time. You say dx dt, that is just velocity. So the mass of the whole thing times the velocity of the center of mass, and take the derivative on this side. Again, each little mass is constant. So it's just the mass times the rate of change ddt of that position. Well, the rate of change of position, that's just the velocity of that bit. So we're just going to add up all the mi vi's, right? Again, to get from here to here, what did we do? We did a d dt, all right, for this whole mess, right? And we did the same thing here. We did a d dt, took the derivative of this whole mess. Okay, and the masses are constant and kick out, so it's just this. Okay, we're going to do that one more time, but this is how we'd find the velocity of the center mass. Then we just move the m total back under here. Velocity of center mass, you just add up all the mi vi's divided by the total mass. Just like to find the position of center mass, it's some of the mi xi's over the total mass. Okay, and if we do this one more time, I'm going to take the derivative again. All right, so if I do a d dt of this guy and a d dt of this guy. Again, mass is constant, it kicks out. The derivative of the velocity with respect to time, that's just the acceleration of the center of mass. So this would be m total times the acceleration of the center of mass is going to be equal to the, again, all the m's are constant. So I'm really just adding up all the masses times the derivative of velocity, the acceleration of each individual bit. All right, we're adding up all those miai's. Okay, if I go ahead and divide through by m total, that'll be my expression for the acceleration of the center of mass. Let's apply that to this case now. Okay, let's apply it to this case. All right, if I did that, isn't it true that for the pulley, right, that would be 3m, and it's not accelerating up and down at all, so that's 0. The stand has a mass of 4m, and its acceleration is 0. It's not going anywhere. Now, m1 has a mass of m, and it's accelerating up. We just found that that acceleration is 11/9 mg. So it's accelerating up at 11/9 g. Sorry, the acceleration is 11/9 g. The force was 11/9 mg. The acceleration was 2/9 g. I'm so sorry, 2/9 g. Sorry. Whoops. 2/9 g. Right, is the acceleration of m, and then this 2m is accelerating down at 2/9 g. So that'll be 2m times an acceleration of negative 2/9 g. Oh, gosh, that's tiny. That's a negative 2/9 g. Okay, divide by the total mass, that's 10m. All right. Hey, every term has an m in it. These are zeros. These two terms go away, right? These are times zeros. They just drop out. Each of these terms has an m, so all the m's drop. So what have I got now? I've got 2/9 g plus 2 times 2/9, negative 2/9 g. That's a minus 4/9. So 2/9 minus 4/9. What's 2/9 minus 4/9? You say, gosh, that would be a minus 2/9 g. But then that's over 10. So the acceleration of the center of mass is minus 2/90 g. Is the acceleration of the center of mass. I can put that acceleration into there, and I'll be able to solve for that normal force. So here we go. Normal minus 10 mg equals 10m times that acceleration of the center of mass, that minus 2/90. G. Okay, multiplying by 10, that'll be a minus 20/90ths if you'd like. Move the 10 mg over here. So here we go. And it'll be 10 mg minus 20/90ths minus 2/9 mg if you want. Okay, let's see here. Let's get this common denominator of ninths. So this would be, multiply this by 9/9. You say that would be 90/9 minus 2/9. That would be 88/9 mg. That's how big the normal force is on the stand, right, from the tabletop. We said before, because our system's accelerating down, we need to end up with a normal force up that is smaller than that 10 mg pulling down, because the center of mass is accelerating down. And sure enough, 10 mg would be 90/9. This is just a little bit less. And so our center of mass accelerates down at negative 2/90 g. And that's it. Okay. All right, that's part E. Okay, now I said there is an alternate way of doing it, right? Okay, so this was like looking at the center of mass and doing our forces. This was treating as our system kind of the whole thing. There's a sneakier way of doing this. I don't know, maybe this is the way that you first saw. Maybe to you it's not sneaky, it's obvious. But here's an alternate approach. We're trying to find the normal force from the floor on the stand here. What we're going to do is, because these parts are accelerating, it would make our life easier if we didn't include those in our calculation. And we just looked at maybe the stand and the pulley as one system. And now I can say, well, the stand and the pulley, they're not accelerating up and down at all. So they have to be in equilibrium vertically, right? Those forces have to balance out. So if I do that, and I make my system be the pulley and the stand, that is an equilibrium. So the sum of the forces ought to be 0, right, up and down. What are our forces up and down going to be? Well, if my system is the pulley and the stand, then maybe I should just draw it again. I was going to say this normal force from the axle, that's not going to show up because that's between the parts of the system, right? Between the stand and that, right? And the wheel. So that'll go away. So what I'll end up with for my force diagram, here's that stand, right? And that pulley wheel. This guy had a mass of 3m. This is mass of 4m. If I just combined, I could say, hey, there's a gravitational force of 7 mg going down, right? There's a normal force up from the tabletop, right? Which is the thing that we're trying to solve for, is that normal force from the tabletop. And you say, what else from outside is even touching this thing? Well, just the two ropes. So there's T1 here and T2 there. Now, T1 we solved for before, okay? We solved for it back here, right? We had our expression for T1 from this, and we went ahead and substituted our acceleration in, and we got that. T2 we can solve the same way. Again, is T1 and T2, are they going to be the same? And you say no, they won't be the same, because if those two tensions were the same, those tensions act at the same R value, the same radius distance out from the axis. So those torques, if the tensions were the same, then the two torques would be the same, and this thing wouldn't accelerate. It would have 0 acceleration. So these tensions are going to have to be different for this to accelerate. So let's calculate. So what I'm going to do is I'm going to do my sigma F equals ma for this combined system in the vertical axis. When I do that, again, we're going to call up positive, down negative. So I'll have n minus 7 mg minus T1 minus T2 equals 0. Those forces up and down have to balance. Normal is going to be balancing out those three together. T1, we figured out before, was 11/9 mg. T2 we're going to have to figure out. I'm going to do it on this paper. all right, because that's right there. If I go ahead and I grab this, and I'm going to use this acceleration for the system that we got before and put that in there for A, I'll have 2mg minus T2 equals 2m times, and our acceleration is 2/9 g. It's the acceleration of that block. So, looking at this then, we could rearrange and get that T2. Now, see, this is going to be 4/9 mg, and I'm going to subtract that from 2mg. So 2 minus 4/9, that would be 9/9 and 5/9. It'd be 14/9. Yeah. So here I'll have minus 14/9 mg. Add up to 0, right? So again, we chose these guys because they're not accelerating up and down, so the forces have to balance out. We got to be in equilibrium. By doing both of them instead of just the wheel or just the stand, I get rid of that normal force from the axle, right? Which is a good thing to get rid of because I'm not necessarily 100% sure how big it is. Actually, I can figure it out from this diagram, knowing it's in equilibrium. But anyway, we're just going to do it this way. So yeah, I just got to solve for n. So we're just going to move these guys together. Hey, minus 11/9 and minus 14/9, that's minus 25/9 mg. 7 mg to get the common denominator of ninths, that would be 63/9. So I'm going to have n moving over here plus 11/9 mg. I'll just do it like this. Plus 14/9 mg. So you say, okay, 25 and 63, that's 88/9 mg. And you say, hey, look, that's the same answer we got using the center of mass. Ta-da! So there's two different ways of doing it. Are there other ways of solving this? I bet there is. I'll bet you could do something tricky with energy, perhaps. Yeah, we could do something maybe with... No. Actually, now that I think about it, probably not. I was going to say, could we do something tricky with no, with like this thing as it rotates, we're gaining we're losing gravitational potential energy to block sink overall, and we're gaining rotational kinetic energy and translational. We could write an equation like that, but I don't think that's going to help us find that force. Because that force isn't doing any work, that normal force, and so it's not going to be involved in any sort of a work or energy calculation. So we can't do it that way. Sorry. But yeah, that's it. So that is that 1985 problem. Okay, solved out. All right.